So I'm very delighted and happy to welcome here Dr. Scott Hubbard here. And let me introduce him and his past successful career in a few sentences. Dr. Scott Hubbard has been a leader in the space exploration for almost 50 years. His career includes a national lab and startup venture, NASA and Stanford University. At NASA, Dr. Hubbard is best known as director of NASA Ames Research Center, the first Mars program director, and his acronym Mars Star. I like it very much. It's from Russian, so as a king of the Mars program of NASA, and the founder of the NASA Astrobiology Institute. As the sole NASA member of the Columbia Accident Investigation Board, Hubbard's work demonstrated the definitive technical cause of the accident. At Stanford, Hubbard has been very active in the emerging entrepreneurial space enterprise, establishing a peer-reviewed journal, New Science, and creating a Stanford Center of Excellence for Commercial Space Transportation. From 2012 to 2023, Hubbard chaired the SpaceX Commercial Crew Safety Advisory Panel. Although now retired from teaching and advising, he continues to serve on various committees for the National Academy, NASA, and other groups. He's an author of the award-winning book Exploring Mars, Chronicle from the Decade of Discovery, and his many honors includes 8 NASA medals, including NASA highest recognition, the Distinguished Service Medal. Dr. Hubbard is also a honorary fellow of the American Institute of Aeronautics and Astronautics. More background is available at his webpage, gscotthubbard.com, and including Hubbard's long life passion for playing music. And I think this is the connection with the Starmus, with the music and science together. Dr. Hubbard, yeah.
Thank you. Thank you for that kind introduction. I'm delighted to be here this morning and look forward to telling you the story of the exploration of Mars over the last 20 years or so, my role in it, a little bit about what we had discovered, and also a little peek into the future of where the science program is going, and maybe just a hint about human exploration at the very end. I'll tell you a lot of stories in 40 minutes or so. I don't have time to go into every detail. A lot of those are chronicled in the book that was just mentioned, where I give a lot more of the so-called backstory of exploring Mars and the role that I've played. Let's make sure we're all on the same page. I'm told that your background could be mathematics, physics, informatics, but there may be a few humanities folks here. So just to put everything in context, Mars is about half the diameter of the Earth. It has about a third of the gravity. The remaining atmosphere is about like Earth at 100,000 feet. So 1% of Earth's atmosphere, and mostly carbon dioxide. And very importantly for engineering, if you want to go to Mars with available launch vehicles, the only window you have is 20 days or so every 2 years. So this puts an extraordinary pressure on the engineers, the managers, to get everything ready, because once that window passes, even the most powerful launch vehicle like the Space Launch System or what Elon claims about the Starship can't get you there. So this is an important thing to remember, that if you miss that window, you're going to wait another 2 years. Beginning 25 years ago or so, we began looking for a way to describe the importance of Mars, what we hope to learn there, in a way that would be accessible to everyone. not just the specialists, but also the average citizen in the U.S., the taxpayer. Mars is important because it's the most Earth-like of the other planets. It is the most likely to have developed life independently of Earth, and we can get there, as I said, every 2 years. But we have another ingredient that makes this such an appealing area, which is water. Water is a cross-cutting issue when you think about exploring this other world, the red planet. Whether it's the solid planet and geology, whether it's past and present climate, whether it's the existence of life in past, maybe today, we'll talk about that, or preparation for human exploration, the presence of water in whatever form, water ice, water vapor, maybe liquid water deep underground, really is what you need to look for to connect the other research themes. So, in coming up with a way to describe the program in a few words, we said, exploring Mars, follow the water. And I'll tell you a little bit more about that in a minute. How did I come to be the very first Mars program director, or as the media dubbed me, the Mars Tsar? It happened out of a failure, or actually 2 failures. So there was the discovery of a Mars meteorite, so-called Allen Hills. You will be familiar with it, your faculty will be familiar with that. And this Mars meteorite, some claimed, showed the residue of fossilized life from Mars. Now, I think most of those claims have not held up under scrutiny, but there do appear to be organic materials there. Nevertheless, this set off a huge push within NASA to get to Mars as fast as possible, and even to bring back samples to see if life actually formed on Mars. So, Mars Climate Orbiter was launched in 98, Mars Polar Lander was launched in 98, and the guy who was the administrator at the time, a very interesting fellow named Dan Golden, said to the engineers, okay, you build these 2 spacecraft to go and characterize Mars, but you got to do it my way. And my way was faster, better, cheaper. Now, anyone who's been involved in managing a major project knows if you get 2 of those, you're doing very well. To get all 3 in the end meant that this project team at NASA, JPL, Lockheed Martin, took foolish risk. You can take managed risk. You can take calculated risk. You have to think about it and do it carefully. But they started taking foolish risk. I'll give you just 2 examples. One, with the Mars Climate Orbiter, they thought they could not afford a second pair of eyes looking at all of the documents, the so-called interface documents. So they just had the junior people, who were cheaper, look at them and thought they were fine. As a result, a mistake was missed, you'll laugh, converting English to metric units. So foot-pounds or poundals into newtons was done incorrectly, and as a result, the spacecraft entered the atmosphere about 60 kilometers too low, and it burned up and disappeared. The second mission, Mars Polar Lander, was missing a line of code, again, because they didn't afford to have all of the people who should have examined the drawings look at it carefully. And so what happened was that here it's coming down, the lander is coming down, the legs go out, the signal goes to the central unit. Central unit says, the legs are out. I must be on the ground. I'll turn off the engines. So it's now in many pieces on the surface of Mars because a line of code was missing. So, faced with this pair of failures, the administrator reached out to me in California. He was at NASA headquarters in Washington, D.C., And this is kind of an Americanism, I hope you bear with me. He put his arm around me and said, "Son, your country needs you. Won't you come to Washington, D.C. and fix the mess?" And there were various reasons why he picked me. That's in the book, we won't go into it. But I picked up everything, got my wife, and we moved in a big hurry, in a few weeks to Washington, D.C., and I started to put the program back together. But I had to come up with some organizing principles. This is a very short version of what I invented. Many of you have heard of systems engineering. This is program systems engineering. How do you put together a decade-long program of missions that will look for past life, that will understand the geology of the climate? Well, you do it basically this way, which is to align science readiness, technology readiness, and programmatic considerations like money, cost, and you work on aligning those three strategies until you come out with a mission queue, and then you iterate this until you focus on a selected mission queue. In addition, to explore another world, it is not sufficient to merely go to orbit. It is not sufficient to merely land. It's very hard. You need to do them in an alternating sequence. You need to do orbital reconnaissance, followed by ground truth understanding, then higher resolution orbital reconnaissance, followed by even better surveillance and measurements on the surface. So this was built into the program. It's no accident, as you will see, that Mars Odyssey was followed by the Mars Exploration Rovers, which was followed by the Mars Reconnaissance Orbiter, which was followed by the Mars Science Lab. That was built in 25 years ago to the program. So this is what we ended up with, this sequence of missions. It's science-driven. Understand the planet as a system by making a series of very careful measurements, as I described, orbiting and landing. Of all the science questions, the first among equals is, did life ever exist on Mars? And to do that, we had a strategy, as I said, called follow the water, because the water is such a key ingredient for all the other science objectives. And also, by the way, we wanted to set the stage for a sample return later on. Almost immediately, there was success in Follow the Water. This is now 24 years old. An image from Mars Surveyor saying that it looked like there were very young areas that for all the world looked also like a flash flood in a volcanic region. So here you have the Mars on the left, the Mars image, and on the right, an image from Earth in an area that was a volcano and then a flash flood. So we started to see immediately that Follow the Water had a really powerful impact and outcome. Mars Global Surveyor also gave us some chemistry, as well as some altimetry measurements. So on the left, you see the result of a laser altimeter, which indicates a very low spot at the North Pole of Mars. And many of the community think this is evidence of a past shallow ocean. There are measurements that are going on right now to test that. And on the right, one of the spectrometers saw this area here, this greenish yellow area. It's about the size of a state in the U.S. Called Connecticut. It's a large region, and this yellow-green color is indicative of a mineral that, at least on Earth, only happens with long contact to water. It's called hematite. That's not important, but long contact to water. So remember that. So my first big decision as the Mars program director was, what do we fly in 2001? It turns out that as we looked at the vehicles that were in preparation, the next lander had so many problems, you just didn't want to fly it. The orbiter looked like it was fixable. And again, faster, better, cheaper failed. We had to go put systems engineering back into the program and see that everything had been checked carefully. As you know, when you launch a rocket, you don't send a repairman out to fix it. You really have to be totally ready to go. So this was then fixed and renamed Mars Odyssey after the famous book and movie Space Odyssey 2001. This was the big discovery. I understand one of your faculty here, we chatted very briefly, was part of making this measurement. It's truly powerful. When the signals from this instrument started to appear, and this instrument is measuring the presence of hydrogen in the top meter of soil. And hydrogen in this form on Mars has to exist almost exclusively in the form of water ice. So what you're doing is getting a proxy measurement by measuring hydrogen for the presence of water ice in the top meter. And what it showed is that all over the planet, very nearly, except right at some places in the equator, certainly at the poles, huge amounts of water ice, far more than anybody had predicted ahead of time. In fact, you see the purplish magenta area there at the North Pole. That indicates up to 80% water ice. So in principle, if you could dig a shovel and melt it, you would have water right there at the North Pole. Now we come to the next big decision, what to launch in 2003. The story of how I chose to pick a lander is in the book. It involved a certain amount of technology, engineering, and politics, because I had to convince people that had suffered through failures that this was, in fact, a reasonable risk to take. And what was built was not one rover, but two rovers, so that if there was a possibility of a random failure, the chance that you would get 1 out of 2 working was still very high. And these are real geological robots. They are Mars, remember Mars Pathfinder, that had a little, very small rover that did a demonstration. This was a full-blown Mars geological rover. And it was designed for 90 days. So when I took a poll of all the scientists and engineers I could find and said, given that these are solar powered and that on Mars the dust is covering everything continuously, how long do you think they will last? And everybody said, a month, 2 months, 3 months, 4 months. I could not find anybody who thought it would last longer than 6 months. So I committed the agency to a success criteria that says that we will get all the high priority science done in 90 sols, which is a Mars day. Nevertheless, Spirit lasted 7 years, Opportunity lasted 14 years on a supposed 90-day mission. So keep that in the back of your mind. We'll come back to that in a second. But first, what we want to do is to go to Mars. So you've been traveling along for 7 months. You drop off the cruise stage. You start entering the atmosphere, and you have to go from 20,000 kilometers per hour down to 0 in 7 minutes. This came to be known in NASA as the 7 minutes of terror. You pop a supersonic parachute about 1.5 kilometers above the surface. It slows you down again. And then you drop off the heat shield that has protected you. And then you drop on a lanyard, a cocoon, which then shortly becomes inflated. Boom. Now, when I first proposed this idea in 1990, 30 years ago, to use airbags, I think everybody thought it was nuts. because you bounce. We probably won't use this for astronauts. Probably. One bounced 22 times, one bounced 33 times, but it was a way of getting a robust and inexpensive landing mechanism on Mars. Turns out you can limit the shock to about 40 Gs, which you can build instruments to survive. And so this technique, which was used now ultimately 3 times, allowed you to land, and once you deflated the airbags, then you could begin to take measurements. You unfolded the pedals. It's a very clever design by the engineers so that no matter which way you landed, you could open the pedals so you ended up with the camera mast vertical. And then you've been traveling on batteries, so the first thing you do is to open the pedals, reacquire solar energy, recharge the batteries, and then this is speeded up greatly from the way that it actually happened on the surface, but all the details are completely accurate. This is an engineering precise rendering of the actual vehicle. And then you see that little paddle there? It's phoning home. What do good robots do? Phone home. Okay, so what have we discovered? What we've discovered is this. This is one example of Spirit and Opportunity's findings. What they found was a type of sediment that looks like a slowly moving fluid over a long period of time. That's all of these waves that you see there. But even more importantly was this. Remember now, you go back to that yellow-green area that's quite large. What that is on the surface is millions and millions of these tiny pebbles of hematite. So we have confirmed orbital measurement, ground truth. Yes, this area apparently was sitting in water for perhaps millions and millions of years. But now coming back to the conundrum, how did a 90-day mission where we thought the solar panels are going to get covered by dust and die end up lasting 7 years or even 14 years? Anybody want to guess what these are? Dust devils, exactly. On Mars, it's like a high desert. So the presence of vortices, dust devils, on any given day is very high. And a few of those happen to pass right over the rover. And it cleaned it off. Totally amazed. In my 50-year career, Mother Nature has only helped me once. And this was it. Usually you're fighting uphill at every turn. So great success. But dust storms occasionally are global, and they last for a long, long time. So this is what the sky looked like, progressively from a nice sharp sun to more and more clouded to where it was just completely this orange-yellow color, obscured from the sun so the solar cells could not recharge. And that meant that Opportunity lost contact, its solar cells couldn't charge, and the mission was officially declared dead in February of 2019, 14 years after it landed. Let's move on to what I call the spy satellite around Mars. Its fundamental resolution is about so big, so it can make very, very precise and highly detailed, high-resolution measurements of the surface. I'll show you an example of that in a minute. Has ground-penetrating radar, does multispectral imaging. Here's an example. You can distinguish what has been done by wind from what has been done by water. And this powerful tool has allowed us to map both the minerals as well as the surface features on Mars since 2005. In fact, the imaging radar, the ground-penetrating radar, has found a glacier the size of another state in the U.S. called New Mexico. And if you melted it It would be as much water as in one of the so-called Great Lakes, Lake Superior. So again, follow the water, huge amounts of water ice. Ice cliffs, just a few years ago, ice cliffs up to 100 meters deep. As you can see, I make this presentation for U.S. audiences, so you'll see occasionally feet instead of meters and so forth. Please bear with me, I'll translate as best I can. But the point is that you have massive ice up to 100 meters below the soil that is something like 2 meters on the surface. Mars Express, a European mission sponsored by ESA, European Space Agency, found evidence of a liquid lake that could be as much as 20 kilometers wide, about a kilometer or so under the surface of Mars. And they announced this now 5-6 years ago. Very tantalizing result. Nobody has confirmed it yet, but if so, it could mean that there is still some liquid water far beneath the surface of Mars. The Phoenix Scout mission was another mission to confirm what we thought from Odyssey. Odyssey said there's water ice all over the planet, but how do you know for sure? So they sent the Phoenix mission in 2007, and it scooped with its arm into the dirt and discovered these little pebbles that, when put in the onboard chemistry set, the onboard laboratory confirmed, yes, this is water ice. So what Odyssey saw, Phoenix confirmed. And then we come to the last large mission that I have had any responsibility for. And this is the so-called Mars Science Lab Curiosity mission. Here you see the family tree of the rovers. The little bitty rover, about 20 kilograms or so on the far right from Pathfinder, the 150 kilogram Spirit and Opportunity, and the metric ton of the Mars Science Laboratory. Very, very sophisticated, powered by radioisotopes, so you don't have to worry about getting dust all over your solar panels. So this probably got another, 10 or 15 years that it can last. So, where did it go? It went to a place called Gale Crater. Gale Crater is like a time machine on Mars. So it was hollowed out maybe 2 billion years ago by a giant impact, then filled in slowly over time. So if you could land very precisely right at the base of the crater and then travel up, you would come to younger and younger and younger material. Get a real time understanding of how Mars developed. And so that's what happened. Here's the entry, descent, and landing. You'll see some differences. One is that it's got guided entry. You see those little jets adjusting, fine adjustment, autonomously, of course. Then the similar type of parachute. And this time, once it dropped off the heat shield, now the airbags wouldn't scale up. So we had to go something called the sky crane. And the idea is you have a rocket-powered helicopter that acts as the mothership and is going to lower the rover down on its wheels. Now, when we were looking for a solution of how do you get a metric ton to the surface of Mars, this was, as somebody called it, the least worst option. It's really tough to get a metric ton to the surface of Mars, but this did the job. It's worked subsequently really well for Perseverance in addition. And so this very, very, first the mothership goes about 1 kilometer off to the side because it still contains propellant, but then this begins the exploration of Mars in detail with a next generation of very sophisticated instruments. Here's some examples. A past habitable environment underneath this oxidized layer. Looks like a briny water cycle. There may, in fact, be still a cycle of evaporation, condensation, maybe snow. and then the process starts again. Methane has been sniffed on Mars, found originally from the Earth, but now validated on Mars by Curiosity. But it's very low in amount. But it's well above the noise of the background, so it's a real result. But its appearance is episodic. It's not predictable. And so there's two explanations. One, abiotic, which is water and volcanism, heat deep within the surface, producing a standard chemical reaction that gives you methane. Or some suggest maybe there is biology going on, because on the Earth, methane comes from our biology of our farm animals in the field. Anybody who's ever lived on a farm knows that cows produce methane. Another fascinating result that is being followed up by a European mission called Mars Trace Gas Orbiter that's looking to understand this. To me, the most powerful measurement that has been made is this one. The instrument on board Curiosity took samples, ground them up, put them in a very sophisticated spectrometer, and while the presence of simple organics, like propane, had already been detected, this was the first to detect really complex organics. I show you. So, for example, instead of benzene and propane, it now has detected kerogen. And on Earth, at least, kerogen is the leftover from decayed plant material. Now, is this proof that there were plants on Mars 2 billion years ago? No, because kerogen is also observed in some small bodies. People that make measurements of certain types of asteroids will see similar types of macromolecules, but it's the first evidence of really sophisticated organic chemistry going on Mars. So where does all this lead us, this last 20 years or so of investigation with all the missions that we put into place 25 years ago? Well, I think the potential that ancient life emerged on Mars is highly increased. I really think that if you pull all the data we've got together, everything that we know about the water, the past water, the present water, the organic materials, the energy, and so forth, it looks like that we now have the ability to go and pick out samples that, if we could bring them back to Earth, would show us what I call the fingerprints of life. What about modern life? Maybe. I mean, the methane results are very tantalizing. Maybe that means there's some biology going on. Deep liquid water, that would be another hint. But at any rate, Mars is far more diverse than anybody ever thought. So the next big step is Mars sample return. This has been recommended twice now by the U.S. National Academy of Sciences as the highest priority for planetary science. And the mission is underway. It's run into some programmatic problems with its cost and schedule. We can talk about that later if you'd like. But let me just show you the scope of this. It's a NASA-ESA collaboration that has a lot of moving parts. People often ask me, well, can't you just put some more rovers down there? Well, you could, but it wouldn't tell you what you really want to know. You want to bring these samples to Earth laboratories to do absolute chronology. And the only way currently to do that is using a particle accelerator. And any of you who have been to CERN or SLAC or any of the national labs around the globe and seeing the size of the instrument, shrinking that to a shoebox for a Mars mission just isn't possible. The second thing is that rather than the few scientists that get picked to be part of the team, you can distribute these samples to hundreds, thousands of scientists with their own instruments. The Apollo samples that were brought back over 50 years ago are still telling us things about the moon. It's hard to believe, but it is a fact. And most importantly, perhaps, is that you can follow the pathways of discovery. Any of you who have worked in experimental science know that you'll have an aha moment. You'll measure something, or you'll take a micro photograph or something and see something you never saw before. And when you do that, you say, wow, I was doing the wrong experiment. We need to go this way. It's very, very difficult to do that remotely on Mars. Doing it with samples on Earth is much more straightforward. So let me tell you what this looks like. The first piece is already there. The Perseverance rover, which landed 3 years ago now, has been busily going around picking up on the order of 30 samples in the end that are worth, in the science community's collective judgment, worth returning to Earth. But to get those samples back requires a suite of other hardware. First of all, you have to get to Mars. As I showed you, that's a 7-month journey involving a heat shield, parachutes, and so forth. And you've got to drill the samples. Perseverance has been doing that very effectively, very carefully, as directed by the Mars science community. And then you've got to land something that can return the samples. So in this version, the samples get put into the nose cone of the so-called Mars Ascent Vehicle. That's a rocket on Mars to come back to come to orbit. These are very sophisticated tubes, meant to last 20, 30 years if they have to. And then you, with those in the nose cone of the Mars Ascent Vehicle, you fire the Mars Ascent Vehicle, which is a solid propellant, back to a waiting orbiter built by ESA. The European Space Agency is providing an orbiter that would receive this small canister, slightly larger than what you would call a football, what I would call a soccer ball, and sealed to protect the Earth from anything that might still be a danger that lives on the surface of Mars. Nobody believes that would be a big risk, but we've only got one planet that we live on at the moment. We have to be extremely careful. And then those samples would land in the desert of Utah. So this very challenging mission with multiple pieces of expensive hardware is currently in preparation. This is what they've been collecting. This is a selection of the first batch of samples taken from an area called Jezero Crater. Jezero Crater is an ancient delta. It is like the fan you would find at the mouth of a major river. All of the consensus of the science community is that if life formed, it would be in some place that had a lot of water, a lot of organics, and that this area, this alluvial fan, this outflow of an ancient river and crater lake would be an ideal spot. So these have been collected. I'm told by the principal scientist from Perseverance that these are, quote, loaded with organics, based on the Raman spectroscopy, for anybody who knows what that technique is. I'm going to conclude now with just a little bit about what was intended to be a technology demonstration, but has turned out to be a fabulous way of doing science and scouting. This is the little Ingenuity helicopter. This was almost a last-minute addition to Perseverance. Weighs about 2 kilograms. It's got counter-rotating blades that reach about 2,500 RPM. That's because the air is so thin on Mars, as I said a while ago, that you have to reach a significant velocity to get the lift, to get the aerodynamic lift. It's a joint effort of JPL, my old center, NASA Ames, that did a lot of the aerothermodynamics, and NASA Langley, that also did a lot of the aerodynamic calculations. And it was supposed to test 5 times It lasted 72 flights. And the last flight was only because it had trouble seeing the surface, and it crashed in too hard and broke one of the rotors. But let me just show you. You can see the little guy right there. I'm going to show you, I think this is flight number 4 or 5. And all it was supposed to do was to go up about 3 meters, go over about 30 meters. In fact, it disappears from the frame for a minute. This is being photographed by Perseverance, obviously. There it comes. And they come back to the exact spot and then land. It's a landing spot. And there, it's demonstrate the first demonstration was named after the Wright brothers of aviation fame. So what did this demonstration end up being? Not 5 flights, but 72 flights. Well, it did a lot of investigation. Look at this panorama that was reconstructed from the images that it took. It was scouting ahead, looking for really, really excellent science spots. And you can see how there was an area from orbit that looked interesting, but before you drive Perseverance over there, you want to see what it looks like up close. So this helicopter shows us how you would have a robot scout for a future mission. And this I really like. This is from, about 50 meters or so. This giant panorama. It reminds me of the movie Lawrence of Arabia. You can almost hear the soundtrack done by Jean-Michel Jarre's father, Maurice Jarre. So there's a Starmus connection for you. Fabulous tool. So people are now thinking about what a science hexacopter would look like that had maybe a 30-kilogram payload rather than just a little less than 2 kilograms. So this is a coming tool. So let me wrap up now, just with a little thought about the more distant future. We know that Mars today, on the surface, is cold and dry. We know that in the past, it almost surely had, for some period of time, abundant liquid water on the surface. Now, in the future, can we go to Mars? Maybe not, I don't recommend terraforming, but go to Mars like we do Antarctica and build a science base to look for the presence of ancient life on Mars? I think we can do this. Thank you very much.
Thank you very much. I think all of us enjoyed this kind of the adventure journey through the beginning of the exploration until nowadays. So we have a time for questions. So there will be some people, maybe myself and others, who will distribute the microphone. So just raise the hands and ask questions.
Thank you very much. I'm curious about how careful are we? You said that we are very careful not to breathe anything like some life or anything from the Mars to Earth. And I wonder how careful we are not to breathe some microbes or something like this from Earth to Mars.
So, excellent question. There is a whole field of, a whole discipline called planetary protection. In 1967, the leading space nations of the world signed the Outer Space Treaty of 1967. And among all the pieces of that treaty, there is one that's devoted to protecting the planet. And it says that the signatories, and the signatories now include 120 countries, everybody but North Korea and Iran, that we will not contaminate other worlds, nor will we allow the harmful contamination of Earth in return. So this has spawned a whole field of study in how do you clean something. Clearly you can bake things to kill all the microbes, but that runs the risk of destroying the spacecraft if it's got plastics and such in it. So other techniques have to be applied. On the return, the current baseline description of the return of this sort of volleyball-sized container is that it will be sealed in the first level of containment, and then a second container will be put in place and welded, an actual autonomous weld holding these pieces together, and then it would be put into the Earth entry vehicle. So all told, I think there was 4 different levels of containment. So that's how careful the U.S. and ESA, NASA and ESA are in being certain that we don't bring back anything harmful.
Thank you very much for a wonderful talk. I have a last excellent question. Have you seen the movie Martian?
Oh, yes.
How accurate is it from scientific point of view in the eyes of an expert like yourself?
Good question. So I'll tell you a little bit of a story there. Andy Weir, the author of the novel, started off writing the book, The Martian, as sort of just a fun exercise for himself. And he posted things online. And after a while, the engineers that do astronaut work at Johnson Space Center started to notice what he was writing. And they started sending in corrections and saying, no, Andy, he can't possibly make that many potatoes, here's a little more accurate. But I was once on at an event in Washington, D.C., and I was sitting back in what they call the green room. This is where you sit before you go on stage. And I was sitting next to Andy. And I said, Andy, great book, great movie, but about the beginning. And he said, I know. I had to get the hero into trouble so I could get him out of trouble. And it's called the arc of the story. What I'm referring to is the very beginning of the movie where they have this terrible storm and it is threatening to blow over the rocket, and it blows an antenna that hits Matt Damon in the head, all of that. And I said, Andy, the air on Mars is so thin that even at the highest measured speed, it would be like... And that's when he said, yeah, but I had to get the guy into trouble. But to his credit, this is maybe more than you want to know, but Ridley Scott, who the director of the movie, who also made the movie Alien, you're familiar with that, noticed the same scientific inaccuracy. So as they were preparing the script and starting to work on the movie, they phoned Andy up and said, Andy, oh boy, I won't try to do a British accent. This isn't right. And he explained, and he said, we're going to make the movie, don't worry. But can you calculate for me what the velocity of the wind would have to be, how many newtons in force it would have to be to actually threaten to turn the rocket over? So the next time you watch The Martian, watch as they're getting ready to take off. There is a wind speed meter, and it shows just like for a tenth of a second the actual number it would have to be to threaten the rocket. So yeah, fabulous movie, greatly entertaining. Beginning is inaccurate, but the rest of it is at least plausible.
Congratulations to all the results and achievements. I just wonder about the heat coming from the inside from the Mars to the surface. At the Earth we have this measurement with geoneutrinos. We understand that about 30-40 terawatts per months of the heat comes to the surface, and life is possible only because of this heat. Yes. So is this heat at the Mars comparable by considering the size of the Mars with what we have at the Earth?
So, very good question. There is a mission that was just completed called InSight. And the InSight mission was designed to measure a couple of key quantities. One was the presence or absence of Mars quakes. And very, very delicate mechanism found that in addition to vibrations from meteorite impact, there appears to be some slight residual tectonic activity on Mars. The other key measurement it was supposed to make was exactly this, which is the temperature gradient versus depth. Now, that tool turned out to not be prepared for the Mars soil that it was in, so they have only limited data. But what it appears to show is that as orbital measurements indicated, Mars, being half the size of Earth, cooled off much more quickly. It aged more quickly. And the residual magnetic traces show that the core maybe is still somewhat molten, but the dynamo, the magnetic fields that we have on Earth from the rotation of the liquid core on Earth disappeared, I'll say, a few billion years ago. So all of that indicates that while there is still a temperature gradient from near molten metal to the surface, which varies at the equator from plus 26 centigrade to a minus 120, this gradient still exists, but is probably heavily modified by, first of all, the lower temperature of the core, and secondly, the type of material that it has to propagate through. So I would say, I just saw the principal investigator for InSight recently, and he said he would have more data coming from his mission about thermal gradients. So I'd say stay tuned, we'll learn more. Yeah.
I have one question quickly related to this in the atmosphere. You said good explanation, but I think that there is a third one. That the origin of the methane is in the burning of carbon meteorites in the atmosphere. It is seen, but when the calculation of the ground and this contribution or concentration of the methane in the atmosphere, it was pretty optimistic. And second one is political questions, because everyone president of the United States is speaking about sending people to the Mars. But everyone said that it will be cut beyond his term presidency. So what are your expectations that it can be real? Because you mentioned that these missions with the return of the Starmus, not with human exploration. Do you have some idea about it? And maybe third one, but you haven't answered. There was a question after the man lands on the Mars, then will we send many people to the Mars? There isn't any different. And there is the idea of Elon Musk that we can warm up the Mars, it's really cold, by exploding the thermonuclear bombs on the surface of the Mars. We have this EPDT agreement on the Earth, we even cannot test nuclear weapons, but some people, as I mentioned, one of them, enough crazy, wants to explode the bomb there just to warm up the Mars. What's your role with that?
Okay, I don't know if I can remember all three, but you can help me out. We'll start with the last one first, which was the politics and the technology of terraforming. This is an idea that has been around a long time. There's a famous science fiction series, books called Red Mars, Green Mars, Blue Mars, something like that. They invoked a different technology using microbes to resurrect the atmosphere of Mars. When I served on the National Academy Committee looking at the whole area of planetary protection, And we didn't have an ethicist on the panel, so we could not consider the question of, is it ethical to go and completely transform the climate of another world? And my own personal, this is just me speaking, is that we need to be very certain that Mars is today free of life. If there is even microbial life on Mars, I would not want to be responsible to go and change the planet for them. You know, it's sort of like the Hippocratic Oath, first do no harm, or, you know, Star Trek, you know, don't interfere. The question about human exploration of Mars, and first the Moon, and then Mars, is an example, I think, of the kind of constancy of purpose that is needed to achieve such an extraordinary venture. The skeleton of the return to the Moon was actually laid out by the administrator named Bridenstine in the previous administration, and the current administration has taken that and expanded it. They have what they call a three-leg stool. One leg that is why we do it. Why would you send humans to the Moon or even on to Mars? And remember, this is from the U.S. perspective. One is for science. A lot of things you can do if you have an astronaut on the surface. Two is for things like technology. It's called national interest, you know, developing new capabilities. And the third is for inspiration. You know, when I was part of NASA every day and would be asked to come and give lectures to middle school, you know, to kids, you know, 10 to 12, 8 to 12 years old, there were two things that would get them excited: dinosaurs and astronauts. So the idea of inspiration of the space program, I think, is a very real thing. And this three-legged stool, I think, is a good one. What I'm trying to do is to get the current NASA leadership to include science much earlier than it was done on the Apollo program, where it was kind of grafted on at the end. But the first question, can you help me? Yeah. So I think you're right. I think that there are abiotic, normal, completely normal explanations for this. What is not understood is why it is so episodic. People have looked at times and said, there's no methane on Mars. And then somebody else makes a measurement later, and then it's appeared. So some kind of cycling is going on that is not understood.
Thank you. So, any other questions?
Maybe one more?
Thank you very much for the talk. My question is about the political discharges in atmosphere of Mars. Did you observe them, or what is the frequency of those? Electrical discharges in the atmosphere of Mars.
Did you say recharge?
Electrical discharges,
Lightnings of Mars or discharge in the atmosphere.
Atmosphere and electrical breakdowns, sparks, or lightning. Did you observe it in your missions?
Mm-hmm.
Let me rephrase. So,
Yeah.
there is any activity in the atmosphere of Mars,
Uh-huh.
like lightning or discharge.
Okay. Yes. Oh, discharge. I'm sorry, I didn't hear it correctly. Yes, they have in fact seen electrical discharge. They've seen weather of various types on Mars. There are high clouds. There appears to be times of precipitation. And so this is what gives the astrobiologists the feeling that the ingredients for certainly the creation of amino acids and other types of more complex compounds are in place. It's just that we haven't seen anything that is definitive on whether or not any of these activities have produced a living system. I think there was one more up here, and and we don't want to hold you all afternoon.
Thank you very much. Very inspirational. But you left it kind of open. Where did this water go?
Yeah.
Well, and why?
Right. So as the planet cooled, the water that had been present under a much thicker atmosphere began to disappear in a couple of different ways. One way is escape to the atmosphere and ultimately escape the planet. Some very, very small, like, hydrogen, helium, and so forth, they will escape. Second part is just freezing, and third part is going underground. So between these 3 or 4 mechanisms, the escape out of the atmosphere as it disappears, because the planet's magnetic field is disappearing. So when the magnetic field disappears, the solar wind is capable of pushing away the remnant atmosphere. As the planet cools, the volcanism goes away, so you do not replenish. That's what I thought you meant, recharge. You do not replenish the atmosphere, and it gets blown away because the magnetic field's disappearing, so it's a concatenated systems effect. And what people wonder is if the Mars Express results indicate that the underground water may still be there, and very, very saline, very salty. But we know on Earth that there are so-called extremophiles that love a very salty environment. So maybe, if life emerged, maybe it went underground. So that's that's the 30-second version of answer. The whole answer is more complex.
Yeah, thank you very much. So I think we can close the discussion, and thank you again very much for your very nice talk, and thank you to drive us into the details of the Mars exploration, and also to have an experience of your own contribution on this exploration.
Okay.
Thank you very much.
Thank you.